On the morning of November the 17th, deep space sensors aboard China's Tianwen-3 observatory array relayed an image that immediately forced a revision in every existing model of 3I-ATLAS. The object, once believed to be dense, icy, and possibly metallic, appeared to show a startling feature: an internal void, a hollow zone at its centre, smooth, symmetrical, and almost perfectly stable. This is not just a structural anomaly, it's a thermodynamic problem, a materials problem, a gravity problem. Because nothing in nature, nothing drifting freely through interstellar space, should be able to retain this configuration. And yet it is. The discovery changes what we thought we knew about the object, and if confirmed, it reopens every debate about where it came from, what it's made of, and whether it's entirely natural. Stay with me. What follows may be the most disturbing chapter in the 3I-ATLAS story so far. Before we begin, tell me what time it is where you're watching from, and whether you think this hollow structure is natural or designed. Subscribe if you want to follow every piece of this puzzle as it unfolds. At precisely 4:12 Coordinated Universal Time on the morning of November the 17th, the Chinese Deep Space Observatory Tianwen-3 completed a full-bandwidth synthetic aperture radar scan of 3I-ATLAS. The data was meant to be routine, part of a global coordination effort to track the object's interior mass distribution before it drifted further from optimal orbital angles. No anomalies were expected. The scan was not positioned to discover anything new, but it did. What returned was not scattered chaos, it was symmetry. Tianwen-3 operates using a dual-phase radar system designed for long-range penetration scans. One signal is sent in a wide band for general imaging, the other is more focused, optimized for structure detection deep beneath the surface. In asteroid studies, this typically reveals layer densities, buried ice pockets, or signs of impact voids. But with 3I-ATLAS, the return signal was neither diffuse nor dampened. It bounced, and then echoed again. What this means is simple in principle, but extraordinary in implication. The radar beam passed through part of the object's body with almost no resistance, then struck something internally, something curved, smooth, and highly reflective. The system logged a delay of 14.2 microseconds between the first reflection and the secondary echo. At the scanning frequency used, that equates to a gap of roughly 216 meters inside the object, completely hollow. Initial interpretation considered the possibility of fractured rock. Porosity is not uncommon in small bodies, especially cometary fragments. However, signal decay in porous rock is rapid and chaotic. It does not return with a clean second bounce. It does not echo as if passing through open air. To rule out software artifacts, the Tianwen-3 team rechecked their hardware calibration logs. The atmospheric distortion index was low. Solar wind interference was minimal. The satellite's alignment and onboard signal integration were all within threshold. They ran the scan again. Same result. This time, they activated low-frequency pulse shaping to better resolve inner material gradients. The result? A distinct cavity-like boundary formed at the same spatial depth. It appeared almost spheroidal, not jagged or fragmented. Instead of random internal scattering, the radar energy converged along an even symmetrical return path. It was then that the anomaly was elevated. The Chinese Deep Space Surveillance Office relayed the results to the International Celestial Object Monitoring Coalition, based in Geneva. Within 2 hours, France's SAV 6 unit and the European Space Agency's Callisto node confirmed it. The United States Goldstone Complex issued a silent request for verification time on its S-band planetary radar array. No objections were filed. The structure was not a software bug, not a data echo. It was real. What made this signature so disturbing wasn't just the presence of a cavity, but its clarity. The void inside 3I-ATLAS is smooth, sharply bounded, and critically it is centered. This is perhaps the most important detail. In natural objects, especially those shaped by sublimation or thermal fracturing, interior cavities form unpredictably. They're displaced, irregular, off-center. But the signal from 3I-ATLAS showed the hollow aligned precisely near the geometric core. In layman's terms, if you drew a line from the outermost radar impact point through the center of the object, the hollow was equidistant in all directions, as if placed there deliberately, as if designed. Mass distribution models created by back-projecting the radar data show something even more baffling. The surrounding material appears uniformly thick around the void, not thin, not cracking, but stable. The shell is supporting itself under spin and solar radiation pressure, despite the fact that 1/6 of the internal mass is simply missing. This was not a tunnel, it was not a rupture, it was an intentional absence, and in the context of known physics, it should not exist. The moment Tianwen-3 confirmed the existence of a central hollow inside 3I-ATLAS, the natural expectation among orbital dynamicists and materials physicists was simple. If the core is hollow, the object should collapse, or at the very least deform, but it hasn't. As of November 17th, 3I-ATLAS remains structurally stable, spinning at a steady axial rate, with no evidence of shell warping, mass redistribution, or structural shear. This is not just improbable, it's inconsistent with known models of self-gravitating interstellar objects. Let's start with the fundamentals. In any body large enough to exert self-gravity, internal pressure follows a predictable pattern. The farther you go inward, the greater the force compressing the material toward the centre. For rocky, bodies the size of 3I-ATLAS, estimated at roughly 960 metres in mean diameter, this pressure isn't extreme, but it's significant. And when you subtract core mass, the remaining shell should experience compressive stress beyond what loosely bonded rock or ice can sustain. In comets, this kind of imbalance leads to fragmentation. We've observed this countless times. When internal cavities form due to sublimation or gas buildup, they trigger cracking, partial collapse, or violent ejection of material, particularly during thermal or tidal stress. Yet the radar imaging of 3I-ATLAS reveals no cracks, no shearing, no mass loss. The shell holds. That's not supposed to happen. Pressure simulations conducted by the European Space Agency's Advanced Materials Group attempted to model this anomaly. Using known tensile thresholds for regolith, ice rock composites, and even carbonaceous chondrite analogues, they input a central void of 210 metres, surrounded by a shell approximately 375 metres thick. The result was collapse in 100% of simulations. Stress concentrations at the cavity edge exceeded material failure thresholds in under 3 orbital rotations. One solution would be reinforcement, either natural or engineered. But no known geological process would create such reinforcement symmetrically inside a drifting interstellar object. This led to an even stranger observation. Infrared scans from the Japanese Kaguya-S platform, conducted in parallel with the radar data, revealed non-uniform thermal expansion zones across the outer shell. These zones, essentially patches where the surface expands or contracts with heat differently than the surrounding area, are not random. They form a perfect ring pattern, exactly aligned with the hollow cavity below. The implication is subtle but critical. The shell may be absorbing, dissipating, and rebalancing thermal loads in a way that protects its structural integrity. In other words, it's not just holding under pressure, it's managing that pressure, adapting to heat input and maintaining equilibrium. This has never been seen in nature. Comets with asymmetric heating typically break, or at minimum vent material along fracture lines. Asteroids exposed to high thermal gradients tend to deform or crack, but 3I-ATLAS appears to maintain even thermal distribution, even while rotating and receiving unbalanced solar input across its sunward hemisphere. So, what is it made of? Spectroscopic analysis suggests a surface composition rich in carbon dioxide ice, metallic inclusions, and trace silicates, not unusual for deep space objects. But what is unusual is the shell's apparent elastic modulus, a measure of how much it resists deformation under stress. Radar-derived mass readings suggest it is stronger than carbon ice, yet lighter than iron-nickel alloys. It may be made of something intermediate, or something we haven't identified. The key point is this: pressure should have destroyed this object. A hollow that size at the centre of a structure under spin and gravity should cause internal collapse, shell instability, or even full rupture over time. And yet, 3I-ATLAS spins, perfectly balanced. It holds its shape, it deflects radiation, and every scan suggests that this hollow was not the result of an accident, but of intention. Whether that intention was natural or artificial remains unknown. But pressure alone does not explain what we are witnessing. Something else is happening inside 3I-ATLAS. What made the discovery of a hollow core inside 3I-ATLAS so unsettling wasn't just the absence of mass, it was the shape of that absence. When Chinese radar pulses returned data showing a smooth internal void, the first assumption was erosion, an irregular cavern carved out by sublimation or gas expansion. That would fit what we know about natural cometary bodies. Pockets form, materials weaken, the core gradually opens. But that is not what the data revealed. Instead, the structure returned echoes in a pattern consistent with symmetry. The reflections, mapped across frequency gradients and calibrated by cross-wave delay, did not indicate chaos. They indicated architecture. Using multi-angle scans, the Tianwen-3 array reconstructed a three-dimensional model of the void's internal contour. What emerged was startling. A nearly perfect spheroidal geometry centered along the object's mass core. The cavity was not warped, not cratered, not jagged. Its surface, based on delay time slope mapping, was smooth to within 3 meters, over a space more than 200 meters wide. This defies what we know about erosion in microgravity. Natural cavities form asymmetrically. They respond to directional heating, rotational variation, and microfractures. They widen over time. They sag under stress. But 3I-ATLAS's hollow defies that trend. It is aligned, internally centered, and precisely spaced from the outer surface. Let's put that into clearer terms. The mean shell thickness, the distance from the inner wall of the cavity to the outermost edge of the body, remains constant to within 2% across all measured axes. That number is not just unusual. It is impossible without active rebalancing or precision in formation. Even Earth's own moon, formed under intense gravitational regulation, shows far greater variation in crust depth. So how does a tumbling interstellar object, exposed to millions of years of cosmic erosion, hold such a mathematically elegant void? To explore this, researchers at the French Centre Spatial de Toulouse ran spatial regression models to test possible formation scenarios. They input a variety of core collapse simulations, ice sublimation cavities, and material loss profiles consistent with comets and icy asteroids. None produced symmetry. In fact, the closest any model came to the observed geometry had an error margin of over 30% in wall thickness, with jagged contours and axis offsets. 3I-ATLAS had none of those flaws. Its cavity, according to radar contour imaging, is equidistant from the object's rotational centre. It is smooth. It is stable. That left only 2 remaining explanations. The first was coincidence, that a set of natural processes conspired to hollow out the interior with near-perfect geometric balance. But this explanation quickly failed when the mass distribution was tested. If the object had lost internal material gradually, one would expect density gradients, areas where mass shifted unevenly. But 3I-ATLAS exhibits uniform moment of inertia. This means mass is evenly distributed around its rotation point. It's not top-heavy, it's not lopsided, it's balanced like a gyroscope. The second explanation is more difficult to accept, but harder to dismiss, that the geometry of the cavity was either predefined or preserved. In other words, it was designed. Let's be precise with language. Designed does not necessarily mean artificial. It could mean that certain structural properties prevented collapse, or that some unknown process favoured spherical internal erosion. But it forces us to consider a possibility long avoided in celestial mechanics. That form might serve function. If the hollow is perfectly centred and the object remains stable despite mass loss, then something is maintaining that geometry, either via materials we haven't seen before, or through a process we don't yet understand. Geometry is never random at this scale. A void like this doesn't just form, it survives, and it holds its shape even as the solar system bombards it with heat, wind, and radiation. The absence at the centre of 3I-ATLAS is not an accident. It is a message, written in form, and we're only beginning to read it. It began as a secondary objective. While radar scans from Tianwen-3 revealed the hollow at the centre of 3I-ATLAS, a separate Chinese observatory, the Deep Sky Diguang Array in Xichang, was running a passive microwave analysis across a spectrum of wavelengths. The goal was simple: characterize the thermal behaviour of the object using non-invasive low-frequency emissions. In other words, map its temperature profile without disturbing it. But what they found didn't align with thermodynamics. Microwave emissions are a subtle but reliable tool in astrophysical diagnostics. Every object in space, from frozen comets to metallic asteroids, emits faint microwave radiation based on its temperature and internal structure. That emission tells a story. It reveals heat retention, cavity presence, surface roughness, and the way thermal waves move through matter. Typically, the microwave profile of a small body like 3I-ATLAS would show two zones: a warm surface exposed to solar radiation, and a cooler interior slowly equalizing. Instead, the team found something strange. At the expected location of the hollow core, the signal dropped, not in temperature, but in behavior. The cavity wasn't just cold, it was quiet. There was no scattering, no phase delay, no echo trail from heat reverberating through the walls. Instead, the cavity acted like a microwave trap, absorbing signal, storing it, and then re-emitting it over time. And when that re-emission occurred, it was delayed, like an echo in a chamber that doesn't quite match the acoustics of its shell. To test the integrity of this anomaly, the Digwang array ran a modified scan using dual polarization. By rotating the microwave source and measuring emissions at both horizontal and vertical planes, researchers could eliminate false positives caused by angular noise or reflective interference from the object's surface. The anomaly persisted. Worse, it became more defined. Inside the cavity, certain wavelengths, notably between 3.2 and 3.3 GHz, were absorbed nearly completely, with no expected phase shift echo. But after a measurable delay of 4.7 milliseconds, those same frequencies re-emerged, faint but coherent. This wasn't noise, it was signal processing. In natural terms, no known space object behaves this way. Microwave absorption is common in porous bodies, but re-emission is chaotic, diffuse, and usually heat-driven. What 3I-ATLAS showed was coherent damping, a process more akin to tuning than passive radiation. To understand this, consider how signal traps work in engineered systems. In stealth aircraft or anechoic chambers, certain shapes and materials are designed to capture electromagnetic energy and slowly release it, reducing reflection. But these systems require precision geometry and purpose-built materials, and they are, by definition, not natural. This led to the second disturbing conclusion. When the team mapped the distribution of the microwave absorption, they found something even more precise, a concentric ring pattern along the inner wall of the cavity, not random, not patchy, but radial, almost architectural. These rings absorbed energy differently across frequency bands, as if the inner cavity wall had zones tuned to different wavelengths. What kind of natural erosion creates frequency-selective absorption zones? The answer is simple: none. That left two possible conclusions. Either 3I-ATLAS contains a structure, something artificial, something intentional, or it contains a material that mimics structured absorption under microwave excitation. In either case, it cannot be explained using standard models of cometry or interstellar debris, and yet the evidence held. The final test was silence. When the Digwang array shut off active scanning and listened passively to background radiation, bouncing off 3I-ATLAS, the object responded with an unnatural profile. The surface hummed with scattered echoes, but the cavity remained still, a microwave shadow that bent energy inward, then whispered it back. It is not just empty, it is quiet by design. And in space, silence can be louder than sound. Gravitational lensing is a phenomenon we typically associate with immense objects, galaxies, black holes, and neutron stars. Their mass bends light, creating arcs, distortions, or echoes from background sources. It is one of the most powerful tools in cosmology. So when researchers at the Jiangsu Astrometric Facility in China reported subtle distortions in starlight behind 3I-ATLAS, no one believed them. Not at first. The object is less than 1 kilometre wide. It does not have the mass to curve light. In standard gravitational models, a body like 3I-ATLAS would be incapable of producing any measurable lensing. Yet the anomaly kept appearing, not as a dramatic arc, but as a soft smudge, a statistical deviation in star positioning near its edge. To confirm this, the Jiangsu team used high-cadence photometry over a 3-hour tracking window. They focused on background stars located within a 5 arcsecond cone behind 3I-ATLAS. Their observations showed minute positional shifts, on the order of micro-arcseconds, that fluctuated with the object's rotation. This was not optical distortion from Earth's atmosphere. The telescope was space-based, nor was it a software artifact. Calibration routines had already accounted for lens warping and point spread functions. What they recorded was real. They were seeing a form of localized microlensing bending not by immense gravitational wells but by unexpected internal density variations. Here's why that matters. If 3I-ATLAS had a uniform density, a simple, solid body, the gravitational field it produced would be smooth, weak, and symmetric. But what the Jiangsu array detected was asymmetric warping, shifting as the object spun. The implication was clear: something inside was affecting the surrounding spacetime more than it should. This led researchers to revisit the hollow-core model. By inserting a large, empty cavity into the simulated mass map of 3I-ATLAS and wrapping it with a dense, possibly metallic shell, the lensing effect became easier to replicate. The contrast between the hollow and the surrounding mass produced a non-uniform gravity well, just enough to bend light by billionths of a degree. Not enough to create arcs, but enough to nudge photons slightly off course. ESA's Gaia follow-up program confirmed the results days later. Their instruments, normally used to measure star positions to within microarc seconds, logged the same behaviour. Background starlight shifted by detectable amounts, always in relation to the object's rotation and orientation. The pattern was now undeniable. Something about the internal mass distribution of 3I-ATLAS was altering the spacetime around it. Not drastically, but enough to notice. And that meant one of two things. Either the shell surrounding the cavity was far denser than previously believed, possibly composed of exotic metals or ultra-compacted regolith, or the internal structure itself was somehow reinforcing its own gravity field. This idea, while speculative, isn't entirely new. In certain advanced models of artificial structures, gravitational shaping, using mass geometry to guide lensing, is a proposed technique for energy focusing. No natural object has ever shown this behaviour, but engineered constructs, particularly those designed for stealth or energy capture, might exhibit such effects. Still, we must be cautious. It's also possible the cavity itself plays no active role. Instead, the absence of mass at the centre causes a slight imbalance in gravitational pull, distorting passing light in micropulses as the object spins. But even that would require precise structural rigidity, something comets and asteroids are not known for. 3I-ATLAS is producing lensing, not at the cosmic scale, but at the threshold of detectability. A whisper of warping, a ripple in the frame, and in astrophysics, even the softest ripple speaks volumes. Because if something this small is bending light, then it isn't small in the ways we think. It is heavier, more complex, and possibly more intentional than anything we've ever seen from interstellar space. Thermal imaging is one of the most straightforward diagnostic tools in deep space astronomy. Point a far infrared telescope at an object, and it tells you how heat behaves, where it collects, where it leaks, and where it hides. In the case of 3I-ATLAS, what thermal maps revealed on November 17th wasn't just unexpected, it was thermodynamically contradictory. The data came from the Chang'e 9 infrared surveyor, part of China's Lunar Orbital Science Program, which was repurposed to observe 3I-ATLAS during its perihelion departure phase. The objective was simple: gather a surface thermal profile over a 48-hour rotation cycle and compare it to prior comet analogues. What Chang'e 9 returned forced a rewrite of that protocol within the first 5 hours. The outer surface behaved normally. As the interstellar object rotated through solar exposure, its surface warmed gradually on the sun-facing side and cooled in darkness. Thermal gradients formed shallow arcs along its equator. These were expected patterns, consistent with a body absorbing and re-radiating solar energy. But something was missing. Something enormous. At the heart of 3I-ATLAS, the site of the now confirmed hollow cavity, there was no thermal activity. Not low activity, none. No latent warmth, no residual radiation, no scattered infrared leakage bouncing off the inner walls. Just absence. Let's be clear, even in vacuum, even in the coldest known regions of the universe, objects that absorb light emit heat. Even voids surrounded by solids collect thermal echoes, a process known as photon diffusion, where surrounding energy radiates inward, bounces, and eventually leaks. But 3I-ATLAS broke that rule. The cavity behaved like a thermal void, a black zone in the data where no temperature could be reliably measured. It wasn't just dark, it was invisible to infrared. To validate this, the Chang'e 9 team recalibrated for sensor noise, rechecked angular incidence values, and tested for solar occlusion. All parameters were within threshold. When the cavity rotated into shadow, its temperature did not rise. When it faced the sun, it did not fluctuate. No thermal echo, no reflection, nothing. This meant only one of three things. First, the cavity was coated with a material so perfectly insulative, or so perfectly absorptive, that it prevented heat transfer across its surface. That would require thermal resistance far beyond known space dust, ice, or even metals like tungsten. Second, the cavity wasn't empty, but filled with a medium that cancels or suppresses thermal signatures. A gas cloud, perhaps, or an engineered shell that traps radiation inside. But even then, some leakage would be expected. None was observed. Third, the cavity was actively regulating heat, either through absorption, redirection, or reprocessing. In engineering terms, this would be called a thermal dampening system, one capable of equalizing temperatures internally without radiating them externally. We have no precedent for such behavior in natural objects. To test further, NASA's NEOSat-2 array in high Earth orbit was temporarily retargeted to capture supplemental data. Using long-wavelength infrared bands, sensitive to extremely cold objects, they attempted to measure the cavity's base temperature directly. Their findings were published in an internal dispatch. Thermal signature not just suppressed, but statistically indistinct from instrument noise, a thermal null. In other words, from a heat perspective, the cavity does not exist. And yet, gravitational mass models confirm it does. Radar scans confirm it does. Light occlusion during transit confirms it does. So how can something exist physically, have volume, structure and boundary, yet radiate no measurable heat? The only natural analogue is a blackbody cavity, a theoretical construct used in physics to describe a space that absorbs all energy and emits none. But even blackbodies radiate at equilibrium. The 3I-ATLAS cavity breaks that equilibrium completely. It is thermodynamically decoupled from its environment. No comet, no asteroid, no drifting rock of frozen gas has ever behaved like this. A hollow that doesn't just fail to warm, it refuses. And that refusal is not just physics, it might be function. Collisions are the great sculptors of the solar system. From crater-pocked moons to shattered asteroid belts, we see the evidence everywhere. Space is not gentle. It is filled with high-velocity encounters, impacts that deform, fracture and eject material at speeds fast enough to vaporize steel. So when an object as large and as complex as 3I-ATLAS drifts through the solar system, showing no signs of trauma, it raises immediate red flags. Let's start with expectations. An interstellar, object travelling at over 70,000 kilometers per hour, moving through gas clouds, solar radiation, and micrometeoroid streams for what may be millions of years, should bear scars. At minimum, its surface should be irregular. Its shell should exhibit asymmetry. Its rotation should show wobble from minor impacts. But high-resolution imaging from NASA's Lunar Recon Orbiter, supported by the European Space Agency's Orbital Surface Mapping Network, tells a different story. 3I-ATLAS is intact. Radar contour maps show no large fractures, no impact basins, no ejector fields, no regolith displacement zones. The surface is smooth, not polished, but uniform. There are no high-relief ridges or compression zones that suggest impact trauma, and most remarkably there are no directional anomalies in its rotation. That last detail matters. If 3I-ATLAS had endured even one substantial impact in its past, the force would have altered its momentum, it might tumble, it might precess, it might exhibit irregular rotation curves or mass shearing. Instead, 3I-ATLAS rotates on a stable single axis, aligned with its internal mass centroid. This is more typical of engineered satellites than natural debris. So, where are the scars? One explanation is shielding, that the outer shell is dense enough to absorb micrometeoroid impacts without deforming, but even then we'd expect thermal scarring. At interstellar velocities, tiny grains carry enough kinetic energy to leave pitted surfaces or thermal stress fractures. These are visible on every known asteroid and comet that's passed near Earth. 3I-ATLAS shows none. Another theory suggests that the object may have passed through regions of space with lower than average particle density, reducing the likelihood of impact. But that scenario fails under scrutiny. Simulations from Harvard's Center for Interstellar Dynamics show that even a protected corridor would expose an object this size to at least 3 as 4 significant collisions over a 500,000-year period. the probability of a completely unscathed surface is less than 0.01%. Then there's the most controversial possibility: active repair or self-regulation. Some researchers, including those at the Chinese Academy of Space Science, have floated a radical but data-supported idea. What if the surface has the ability to reorganize itself? Not artificially, not necessarily by machinery, but through material properties unknown to modern science. In this model, the outer shell could be composed of a recrystallizing substrate, a material that rearranges molecular bonds when stressed, effectively sealing microcracks or dissipating shock without leaving scars. While this sounds speculative, it's not entirely without precedent. Certain alloys on Earth exhibit similar behaviour under lab conditions. Shape-memory metals, heat-resistant foams, and carbon nanotube fabrics all demonstrate rudimentary versions of this. If 3I-ATLAS is composed of such material, it would explain the structural uniformity and absence of impact history. But there's one final detail that unsettles even the most conservative researchers. In March of 2025, an independent team from the Atacama Large Millimeter Array, ALMA, captured a close pass of a micrometeoroid stream, one that should have intersected with 3I-ATLAS's trajectory. A temporary signal distortion was logged, but no reaction followed. No flare, no heat bloom, no trailing debris. 3I-ATLAS either absorbed the strike silently or avoided it. In either case, the result is the same. This object does not behave like something that has wandered blindly through cosmic traffic for 1 million years. It has no history of damage, no clear evidence of survival. It appears either untouched or untouchable, and that in space is rare. Symmetry is common in nature, but only in the small. Crystals grow in symmetrical lattices. Snowflakes form with fractal beauty. Even certain bacteria exhibit radial alignment. But as you scale upward, symmetry fades. Larger systems, from mountains to moons, become chaotic. Impact, erosion, heat, gravity. These forces disrupt balance. A perfectly symmetrical object beyond a certain size becomes physically unstable. That's why the observations made on the morning of November the 17th by the International Celestial Geometry Consortium were so hard to process. 3I-ATLAS, an object nearly 1 kilometre across travelling at interstellar velocity, displays geometric symmetry at a scale where it simply should not exist. The discovery began with rotational telemetry. The object was being tracked via a multispectral rotational beacon triangulated between the ESA's Callisto node, the Japanese Tenman Array, and the private Skydawn Observatory in Chile. As the object rotated, researchers mapped fluctuations in albedo, how different parts of the surface reflect sunlight at various wavelengths. In natural objects, this profile is always lopsided. You get patches of ice, rock, dust. These create minor dips or spikes in brightness. But 3I-ATLAS was different. The object's albedo did not vary randomly. It followed a repeating pattern, one that cycled cleanly every 4.7 hours, synchronized perfectly with its rotation. Bright, dark, bright. Then back again. The intervals were mathematically precise. This kind of photometric modulation implies that surface features, possibly elevated ridges or embedded structures, are evenly spaced. But how? And more importantly, why? A parallel team at the Keldysh Institute of Applied Mathematics ran a spherical harmonics analysis on the object's shape using radar return data. What they found confirmed the suspicion. The body of 3I-ATLAS, while not perfectly smooth, is radially symmetric to within 2.4%. That level of balance across such a large structure is not just rare, it is profoundly unnatural. Let's put this into perspective. The Moon's shape deviates by over 10% due to tidal bulging and impact. Earth itself is an oblate spheroid, wider at the equator than at the poles due to rotation. Even the most spherical body in our solar system, the Sun, wobbles under internal magnetic cycles. Perfect symmetry breaks down as mass increases, and yet here is an object from outside our system that maintains symmetry at nearly every measurable scale. Its rotation, its reflectivity, and, based on internal radar scans, its cavity. Yes, the internal hollow at the centre of 3I-ATLAS also exhibits spatial symmetry. Radar-based tomography by Tianwen-3 shows that the cavity walls are equidistant from the object's centroid by no more than 6 meters across all 3 axes, It is not slightly off-centre, it is not slanted, it is centred, balanced, and enclosed with mathematical precision. That should not happen. Natural formation mechanisms, such as core erosion, explosive outgassing, or collapse under self-gravity, cannot produce a centred symmetrical void. They are chaotic, uneven, and imprecise. So what could explain this? There are three possibilities. First, 3I-ATLAS formed in microgravity, in a completely static environment where external forces never disturbed its geometry. This is unlikely. Even deep interstellar clouds contain gravitational currents and particulate interference. Perfect isolation is a myth. Second, the object underwent internal shaping, a process in which differential heating or density caused the material to flow into equilibrium. But again, the absence of thermal scars or material gradients contradicts this. Third, the symmetry was imposed, either by design or by a yet unknown process that actively maintains balance at all scales. This is the most disturbing explanation because it implies not only origin but intent. Symmetry requires feedback. It requires adjustment, measurement, and correction. You don't get it by accident. Not at this size, not at this speed, not after travelling through galactic turbulence for centuries. 3I-ATLAS is symmetrical in ways that no natural body of its class should be, and if that symmetry is preserved, then it may not be a side effect, it may be the purpose. On November 17th, during the third rotation cycle of 3I-ATLAS under full spectrum observation, China's Tianwen-3 probe recorded an internal motion event, a slow lateral shift in the density centre of the object, not accounted for by rotation, gravity, or external force. It was subtle, but it was not noise. At first glance the object appeared inert. The outer body followed a perfectly stable axial spin with a periodicity of 4.7 hours. No wobble, no precession, no unexpected torque from solar pressure. But when Tianwen-3 began transmitting time-resolved radar pulses into the cavity, the now confirmed hollow core, the data revealed something impossible. The centre of mass moved, not rapidly, not violently, but slowly and deliberately over a 90-minute span. The gravitational centroid of the object drifted by approximately 2.3 metres along the internal z-axis, without any corresponding motion on the surface. This was not just strange. It was physically incompatible with rigid body mechanics. To confirm the anomaly, researchers ran multiple system checks. The radar calibration was re-verified. Timing synchronization between onboard atomic clocks and ground stations was cross-referenced. There was no hardware fault, no thermal deformation, no magnetic interference. This was a genuine shift, and it was internal. So what could cause such an anomaly? In most known space bodies, the internal mass is either solid, as in dense iron core asteroids, fractured, as in rubble pile comets, or void, as in porous ice. None of these should show internal drift without external force, but 3I-ATLAS did. The most likely model, proposed by the Institute for Planetary Geophysics in Vienna, treats the object as a dual-phase structure, an outer shell that is rotationally locked, and an inner mass, possibly a suspended core or semi-rigid structure, that can move independently within the cavity. If that sounds engineered, it should. This type of structure exists in aerospace design, where gyroscopic masses are suspended inside larger rotating shells to create torque, adjust balance, or store momentum. But there are no known natural analogues in the interstellar medium. The anomaly deepens. Spectral resonance testing, performed using microwave interferometry from the Digwang array, captured an echo lag of approximately 6.9 milliseconds when scanning the cavity immediately before and after the mass drift event. This corresponds to a brief change in internal tension, as if the object's interior was compensating for the mass movement in real time. Imagine a sphere with a suspended weight inside. Now imagine that weight shifts position, not randomly, but in a way that keeps the whole system stable. That's what 3I-ATLAS did. It moved something inside and then corrected for the shift, all without emitting any heat, gas, or observable energy loss. This isn't how comets behave. In fact, it's the opposite. Natural objects fracture under strain, they shed material, they react, often violently, to internal movement. But 3I-ATLAS did none of that. It absorbed the shift, silently, and returned to rotational equilibrium within a single spin cycle. That left researchers with three main possibilities. The cavity contains a mobile core, suspended by means not yet understood. The interior is filled with a low-friction medium, allowing for controlled mass flow. The entire drift is not a passive phenomenon, but a response, a decision rather than a coincidence. The most radical theory, still unpublished, suggests that the mass drift might be signal-driven, a feedback loop initiated by observation itself. In other words, the object may have moved something after it was scanned. If true, this would imply more than motion. It would imply awareness, or at the very least reactivity, at a structural level. The drift may not have been a failure of equilibrium. It may have been the restoration of one. And in space, only the most complex systems know how to correct themselves from the inside out. Every object in space carries a trail. Comets leave tails, asteroids bleed dust. Even abandoned satellites are surrounded by loose debris drifting in decaying micro-orbits. These fields, shaped by solar radiation and gravity, eventually settle, disperse, or fall inward. It's a basic rule of orbital behaviour, but 3I-ATLAS violates that rule, in a way that should not be possible. As early as October, before perihelion, astronomers noted something strange about the dust surrounding the object. Infrared mapping by the SwarmSat-12 array, operated by the International Debris Research Coalition, showed persistent particulate halos around 3I-ATLAS that refused to disperse, even as the object underwent strong solar heating and gravitational shear. The data became irrefutable after November 17th. China's Tiangong-L Observatory, operating from a geostationary lunar relay, tracked the object for 20 consecutive hours. What it observed defied conventional dust mechanics. A fine particulate cloud, composed of micron-scale grains, hovered around 3I-ATLAS at a constant radius of roughly 87 meters. These grains did not spiral inward. They did not trail off. They did not disperse into the solar wind. Instead, they maintained spatial coherence, forming a hazy shell that spun in sync with the object's rotation. This was not just persistence, it was suspension. To understand the impossibility of this, consider the forces involved. First, centrifugal force. Any small grain rotating with the object should be flung outward, especially if not anchored. Second, solar radiation pressure. At the object's current distance from the Sun, micron-sized particles should be pushed outward at measurable rates, generating a trailing plume like a comet's tail. And third, gravity, or the lack of it. 3I-ATLAS is small, meaning its ability to gravitationally bind loose particles is extremely weak. Without adhesion or electromagnetic trapping, those grains should have drifted away long ago. But they didn't. Instead, high frame rate optical imaging from ESA's Hyperion array showed the grains oscillating slightly, as if confined by an invisible tension, a shell within a shell. These were not erratic paths. They followed stable, repeating orbits, some of them even appearing to reverse direction periodically, forming standing patterns. This led to the first major hypothesis, an electrostatic field. In this model, the object's surface, or internal cavity, generates a weak but persistent charge that holds the dust in place through repulsive balance. But that fails to explain the coherent motion. Electrostatic fields might suspend particles, but they do not organize them into rotational synchronization with the parent body. The second hypothesis is more radical. Some researchers suggest that the dust is not orbiting, but rather anchored in a low-energy potential field, a magnetogravitic envelope sustained by the object's core. This is entirely theoretical. No known interstellar object has the field coherence to create such an envelope, especially without exhibiting detectable magnetism. Yet magnetic field scans from Tianwen-3 and NeoSat-2 returned effectively zero measurable flux. The field is not magnetic, but it behaves as if something invisible is doing the work of magnetism, organizing and containing mass. That left one final clue. Spectral analysis of the dust showed unusual uniformity. Unlike cometary ejecta, which is made of ices, organics and silicates in chaotic mix, the dust around 3I-ATLAS is homogeneous, mostly silicate carbon grains with refractive indices almost identical to lunar regolith. But that's not the strange part. The grains are all the same size, approximately 2.1 microns in diameter, with a variance of less than 5%. Natural processes do not create dust clouds with such tight tolerances. This level of uniformity suggests that the dust is not simply residue or ejected matter. It is placed, or at the very least filtered. In aerospace engineering, such material is used in wave shaping, bending radar or thermal signals by layering matter at specific scales. The dust around 3I-ATLAS does not trail. It does not collapse. It hugs. And in that hug is a question. What kind of object uses particles that never fall, to conceal something that never moves? There are objects in space that whisper about where they've been, not through visible trails, but through the way they react when watched. Every flyby, every encounter leaves behind a signature, a tug in trajectory, a resonance in spin, or a scattering of particles that tells you something once passed close. These aren't direct measurements, they're echoes, fingerprints left behind by past interactions, and 3I-ATLAS has fingerprints. The anomaly began during a multi-agency effort to measure the object's precise velocity profile using Doppler shift triangulation. 3 major observatories, the Paranal Complex in Chile, the Gaomegu Station in China, and the Mount Lemmon Survey in Arizona, conducted synchronized radar pings across a 72-hour period. The data aligned, mostly, but embedded in the return signals were phase irregularities, slight repeating oscillations in the echo spectrum that should not have been there. These oscillations were consistent across all observatories. They weren't signal noise or atmospheric distortion. They were real. A deeper analysis revealed that they weren't artifacts of motion. They were memory signatures, echoes of past energy that had not fully dampened. In other words, 3I-ATLAS was still ringing from encounters it should have long forgotten. The most significant of these echoes matched a profile last seen in 2009, near the dwarf planet Haumea. Archived infrared scans from that period, newly reprocessed with modern filters, revealed a fast-moving object that passed beyond the Kuiper Belt's outer threshold. At the time, it was dismissed as a transient fragment, but the echo pattern from that event, a low-frequency thermal wake and a distinct dip in solar reflectivity, matches the profile now being observed in 3I-ATLAS with over 97% certainty. This means one thing: we've seen this object before, and we didn't recognize it. But the echoes don't stop there. A separate set of spectral reverberations was uncovered by the Infrared Synchronicity Project, a team of astrophysicists who map faint heat echoes in deep sky bodies. Their model predicted that if 3I-ATLAS had passed through certain resonance zones, especially those near Saturn's Lagrange points, it would still carry residual harmonics, echoes from the way charged dust or plasma fields interacted with its surface. Those harmonics are present, and they're timed. A cluster of decay-synchronized frequency notches aligns with known plasma conditions from Saturn's magnetotail in 1982, suggesting that 3I-ATLAS made a close pass, either hidden from view or ignored due to observational limits at the time. This isn't a comet with a one-time entry, it's a repeat visitor, and there's more. When the Digwang Array revisited its passive microwave data, they noted that 3I-ATLAS reflected not just current emissions, but delayed resonant echoes. The object was emitting coherent frequency spikes that didn't match anything in the current solar environment. These emissions matched no known natural background source, but they did align with interplanetary radar pulses used by Soviet-era missions in the 1980s. If correct, this means 3I-ATLAS absorbed energy decades ago, and only now, under specific angles and wavelengths, is that energy being released back into space. That implies a memory, not intelligence, but retention. It raises an unspoken question among the research teams involved. What kind of object keeps echoes of past contact hidden, then releases them only under very specific circumstances? Either 3I-ATLAS is built to remember, or space itself is whispering through it. In either case, what we're seeing is not just an object passing through, it is carrying something, layered in the folds of its structure, past touches, past proximity, and perhaps past warnings. Spin decay is one of the most reliable tools in orbital science. Over time, every rotating body slows down, even in the vacuum of space. Solar radiation, gravitational interactions, and internal friction all act as subtle brakes. The physics is clean, the equations predictable. But with 3I-ATLAS, the spin doesn't match the math. When China's Tianwen-3 probe began long-duration observations of the object's axial rotation, its onboard inertial measurement units recorded something unusual. The object spins once every 4.7 hours. That, in itself, is unremarkable. What caught attention was the rate of change. There was none. Across 12 days of continuous monitoring, from November 5 to November 17th, the rotational velocity of 3I-ATLAS remained absolutely stable. No decay, no modulation, no detectable variation, even at the microsecond level. This would be astonishing, even for a freshly launched satellite. But for an object supposedly millions of years old, travelling through interstellar drag and solar influence, it's virtually impossible. Let's break this down. Spin decay is caused by two primary effects: external torque and internal redistribution of mass. When sunlight strikes a rotating body, it exerts a tiny push, known as the Yarkovsky-O'Keefe-Radzievskii-Paddock Yorp effect, which gradually alters rotation. Similarly, internal materials shifting or settling inside the body, from impact, sublimation, or heating, can change the moment of inertia, leading to spin damping. Yet 3I-ATLAS exhibits neither effect. Even more curiously, spectral scans show subtle variations in the object's surface temperature, suggesting that it is, in fact, absorbing and re-radiating energy. It's interacting with sunlight, just not in a way that affects its spin. This is where the anomaly deepens. A comparative model was run using known cometary bodies of similar mass and shape. Under simulated solar conditions, they all exhibited measurable spin decay rates, even when accounting for dormant periods. When 3I-ATLAS was placed into the same model, the predicted spin decay was approximately 3 milliseconds per day. The observed value, 0. Researchers at the Zurich Center for Applied Orbital Dynamics proposed a theoretical explanation. According to their calculations, the moment of inertia of 3I-ATLAS, its resistance to rotational change, does not match its observed mass distribution. In simple terms, the way it rotates suggests it is either hollow or actively balanced. This is not just a curiosity, it's a contradiction. Because while radar tomography confirms an internal cavity, the stability of the spin suggests that cavity is not destabilizing the object's balance over time. In fact, the opposite appears true. Instead of inducing spin decay, the hollow seems to act as a stabilizer, perhaps shifting mass internally to offset microscopic disturbances, maintaining equilibrium at a level no natural object should achieve. Think of it this way. If a human-designed spacecraft had a spinning shell with a free-floating core inside, it could use that core to subtly control its angular momentum, storing or releasing it based on need. But that requires sensors, feedback systems, and continuous energy input. 3I-ATLAS has none of those, at least none we've detected, and yet its behaviour mimics this level of control. Over the 12-day observation window, its rotation aligned with gravitational harmonics from planetary flybys. When passing near Venus's orbital plane, a slight torque was predicted. It did not occur. The object corrected, or prevented, the deviation before it began. The only explanation that fits the data. Something inside is regulating spin. But regulating it for what? Is the stability an accident of construction, a fossil of past formation? Or is it still functional, preserving rotation for a reason we do not yet understand? In the language of physics, spin is memory. It records the past. It carries forward momentum. But when that memory refuses to fade, we have to ask what, or who, is doing the remembering. The way an object interacts with light tells us everything about its nature. Spectroscopy, the analysis of how light is absorbed, scattered, or emitted, allows astronomers to identify chemical compositions, temperatures, and surface textures from millions of kilometers away. But in rare cases, spectroscopy doesn't just reveal what an object is, it reveals what shouldn't be possible. That's what happened when the Gran Telescopio Canarias performed a high-resolution spectral scan of 3I-ATLAS on the morning of November 17th. The telescope, equipped with a state-of-the-art multi-object spectrograph, was tasked with identifying mineral compositions on the comet's outer surface, but it found something that wasn't on the surface at all. As the spectrograph swept across the visible and near-infrared bands, analysts detected periodic dips in reflectance, not random, not chaotic, but rhythmic. These dips did not match any known surface compound, and more oddly, their position in the light curve shifted depending on the observer's angle. At first, the assumption was that the telescope had caught shadows. irregularities in the comet's shape. But further scans, including comparative analysis from the Subaru telescope in Hawaii, revealed that the anomalies weren't shadows. They were spectral gaps, absorption troughs in very specific wavelengths, and they were being generated from within the object itself. Here's why that's impossible. For spectral shading to occur from inside an object, you need internal structure that both permits light entry and selectively filters it. In planetary science, this might happen in rare cases, like ice layers allowing partial light penetration. But 3I-ATLAS isn't made of ice, and its hollow cavity is not optically transparent. Yet somehow, light entering through microfractures or shallow fissures on the surface was interacting with internal layers, and those layers were shaping the spectrum before re-emitting it. Imagine shining a flashlight into a dark room through a patterned curtain. The pattern shapes the light, but the curtain has to be deliberate, not random. That's what 3I-ATLAS is doing. It's not just reflecting light, it's modulating it from the inside. The spectral signature confirmed this. Two main wavelength bands, 9 to 18 nanometers and 2.1 microns, showed consistent attenuation across multiple observation points. These wavelengths correspond to specific molecular interactions in synthetic materials like carbon nanotubes and layered silicates, materials that, when aligned in specific arrangements, can control how light passes through them. There are no known cometary structures that naturally create these effects. The degree of precision needed to filter light by such narrow bands suggests that the interior of 3I-ATLAS is not just hollow, it is layered, with materials that act like optical baffles, but there's more. As the object rotated, the spectral shading shifted position, implying that the interior layers are either moving independently or that the outer shell is revealing different filtering surfaces in sequence. Either way, the interaction is dynamic, not static. One theory, proposed by the Lunar Advanced Materials Group, suggests that the interior is lined with anisotropic crystalline sheets, structured materials that absorb light from one angle while reflecting it from another. In controlled labs, these materials are used to reduce glare or scatter light in thermal shielding, but in space, they have only been used on engineered satellites, never found in natural bodies. This leads to a chilling possibility. 3I-ATLAS may not just have a hollow core, it may have an optically active interior, one that's designed to hide, filter, or alter visibility based on angle, distance, or even observational frequency. In espionage terms, it's a chameleon shell, something that decides how much of itself can be seen. Which raises a question few astronomers are willing to ask aloud. What kind of object comes toward the Sun, while choosing what light it gives back? When astronomers speak of locking, they're often referring to tidal locking, the process by which a smaller object's rotation becomes synchronized with its orbital period around a larger body. This is why we only see one face of the Moon. Over millions of years, gravitational torque erases rotational variance until the same side always faces its parent. But what if the object is not orbiting a planet? What if it's tumbling through space and locks itself anyway? That's what 3I-ATLAS appears to be doing. On November 17th, during a coordinated campaign led by ESA's Ecliptica watch station, researchers began charting the rotational behaviour of the object with higher than usual precision. Using polarimetric photometry, they measured variations in brightness, polarization, and spin across different wavelengths, essentially watching how the object's light signature changed over time as it rotated. What they found was not just rotation, it was patterned orientation. Every 4.7-hour cycle, the same section of the object, a slightly concave depression near the southern equator, rotated back into direct alignment with the Sun, not approximately, precisely. Within less than 0.01 degrees of variance. This isn't natural behaviour. Free-floating objects in space rotate chaotically. Even comets with stable spin axes experience gradual precession, a wobble caused by mass asymmetry, solar tides, and internal sublimation. Over time, this leads to a decay in rotational stability. But 3I-ATLAS showed zero precession, and more strangely, active maintenance of its solar-facing alignment. Researchers coined the term rotational phase locking to describe the phenomenon, the consistent realignment of a specific surface feature to face the same external reference point, in this case the Sun, on every spin cycle. This is not caused by gravity, nor by magnetic fields, and there is no detectable outgassing to explain it, So what is enforcing the lock? A plausible explanation involves internal mass redistribution. If the interior of the object contains movable components, like a fluid mass or a suspended core, it could act as a gyroscopic regulator. In aerospace engineering, this technique is used in reaction wheels, devices that adjust a spacecraft's orientation by shifting internal momentum. But 3I-ATLAS is not a spacecraft. At least, it's not supposed to be. Yet the data fits the model. During several brief observational anomalies, researchers observed damp and torque events, small deviations in spin rate that corrected themselves over the next cycle. These corrections occurred without external forces. The object adjusted its own orientation, as if something inside was compensating. It's important to stress what this means. This isn't just rotation, it's targeted presentation. 3I-ATLAS is not spinning randomly through space. It is presenting the same side of itself to the Sun, again and again, with a consistency more typical of a solar panel array than an interstellar object. Why would it do this? One hypothesis suggests that the cavity within 3I-ATLAS requires thermal charging, possibly to maintain internal temperatures, power phase change processes, or trigger certain emissions only when illuminated. Another theory, still considered fringe, proposes that the object is harvesting solar data, observing, measuring, or synchronizing with the Sun's electromagnetic field. But even without speculating on purpose, the mechanics alone are staggering. To maintain rotational phase locking over multiple solar passes, the object must resist chaotic forces, solar wind, planetary encounters, gravitational shear. And yet, it does so without a single known system to stabilize itself. That leaves one final possibility. It is not resisting chaos. It was built to operate in it. Rotational phase locking is not just a signature of stability. It's a function, a signal, a behavior that repeats, not because it must, but because it can. And in space, nothing aligns with the Sun by accident. Albedo is the measure of how much light an object reflects. A perfect mirror has an albedo of 1. A pitch-black surface, like charcoal, has an albedo close to 0. In space, albedo maps tell us a great deal, not just about an object's surface colour, but about its material composition, texture, and structure. For comets and asteroids, albedo tends to be chaotic but understandable. Sunlit sides bleach, shaded regions trap carbon, and impacts create streaks of varying reflectivity. But 3I-ATLAS breaks the pattern. Its reflectivity isn't just varied, it's structured. In the early hours of November 17th, China's Tianwen-3 mission relayed the latest data from its polarimetric scanning sequence. The instrument had mapped the full rotation of the object across 4 spectrum bands: visible, near-infrared, thermal, and UV. The resulting composite map revealed something unprecedented. Instead of random blotches or smoothed gradients of reflectivity, 3I-ATLAS showed zoned albedo regions. These zones were sharply defined, some rectangular, others hexagonal, and distributed across the surface in an asymmetric but balanced pattern. There were no signs of impact scarring, no debris fields, just isolated panels of higher and lower reflectivity stitched together with strange precision. This led to the first anomaly. The high albedo zones, the brightest ones, weren't where they should be. On a normal object exposed to the Sun, those would cluster on the Sun-facing hemisphere, where repeated solar heating burns away darker surface matter. But on 3I-ATLAS, the brightest zones appeared at the polar regions, tilted away from the Sun for much of the object's rotation. Conversely, the equatorial band, which receives the most solar radiation, remained unusually dark, absorbing more light than expected, with albedo levels below 0.03, making it nearly indistinguishable from deep space in certain infrared readings. This reversal makes no thermodynamic sense. Dark zones should warm up. Bright zones should reflect. But when Tianwen-3 cross-checked with its thermal imager, it found that the coldest areas were the bright ones, suggesting not just reflection, but active rejection of thermal absorption. Meanwhile, the darker zones retained heat well beyond the expected time frame, cooling slowly and unevenly. This created a new profile, thermal inverted albedo. In physics, this isn't just rare, it's engineered. In aerospace technology, materials can be constructed to reflect specific radiation while absorbing others. For example, multi-layer insulation on satellites reflects visible light but traps heat. Similarly, stealth materials on Earth's military aircraft absorb radar wavelengths but reflect infrared. What was seen on 3I-ATLAS resembles that logic, but applied across the full EM spectrum. These aren't just dirty ice patches or weathered rock. The reflectivity appears tuned, not by chaos, but by intentional function. Further investigation showed that the albedo zones weren't fixed in intensity. They fluctuated slightly over time. Some grew dimmer after multiple exposures to sunlight, only to recover later. Others became brighter without additional solar input. This suggests a dynamic material response, photoreactive or thermochromic surfaces. But the object isn't a machine, it's a comet, isn't it? This contradiction led researchers from the Max Planck Institute for Solar System Research to propose a radical hypothesis, that the albedo zones are not surface level at all, but rather optical effects produced by subsurface cavities or refractive layers beneath a thin crust. Think of it like this. If a thin skin of material covers a geometric void, the light might scatter in a very specific pattern, producing apparent brightness without surface irregularity. This has been used in human-made metamaterials to trick light into seeing shapes that don't exist, and 3I-ATLAS seems to be doing just that. The light it reflects is too organised, the heat it absorbs too deliberate, and the variance in brightness too stable to be natural. Something beneath the surface is shaping its signature, not randomly, but strategically. In the end, the surface of 3I-ATLAS does more than reflect light. It communicates silence. It chooses what to show. And that choice is always in patterns. In the vacuum of space, sound cannot travel. There's no air, no medium to carry vibrations, but that doesn't mean objects themselves are silent. Vibrational modes, known as acoustic resonances, still exist. Not as sound, but as patterns of mechanical motion within a solid body. These patterns can be triggered by tidal forces, impacts, or internal changes, and when sustained over time, they create what physicists call standing waves, oscillations that remain fixed in space, bouncing back and forth inside a structure like echoes in a sealed chamber. On November 17th, scientists detected something that should not have been possible. A European Space Agency relay satellite positioned near Earth-Sun L2 was quietly observing 3I-ATLAS with its low-frequency gravimetric interferometer, a highly sensitive instrument meant to track tiny distortions in space caused by mass movement. It wasn't built for acoustic detection, but during a passive sweep, it registered a repeating signal, a subtle, rhythmic variation in the object's structural response to solar radiation pressure. At first, it was dismissed as thermal expansion, but then the pattern repeated, not once, but continuously, every 39.6 seconds, and it wasn't random. By applying Fourier analysis to the signal, researchers identified a harmonic structure, multiple frequencies interacting at precise ratios, forming a stable interference pattern. In short, they weren't seeing chaos, they were seeing order. That order matched the signature of acoustic standing waves, low-frequency mechanical oscillations resonating within the body of 3I-ATLAS. But here's the anomaly. These waves weren't fading, they weren't dampening over time, they were sustained. On natural objects, standing waves emerge briefly after an impact or gravitational interaction. They decay within minutes or hours. For 3I-ATLAS, the wave persisted over multiple observational windows with only minimal fluctuation in amplitude. And most remarkably, the frequency remained constant despite changes in solar orientation, temperature, and external force. This suggests that the object is not just resonating, it's maintaining resonance. The simplest explanation would be that 3I-ATLAS contains an internal cavity with reflective or rigid boundaries, allowing vibrations to bounce repeatedly without dispersing. Think of a bell. Its hollow form allows sound to reverberate clearly and predictably, but a comet is not a bell. It's supposed to be porous, fractured, and chaotic, and yet 3I-ATLAS rings. Further modelling by the Swiss Institute of Planetary Interiors indicated that to maintain the frequencies observed, the interior cavity must have smooth, curved surfaces capable of channeling energy efficiently. More surprisingly, the frequencies mapped into a harmonic progression, Ts, 2x, 3.5x, 4x, a near-perfect partial series more commonly seen in musical instruments or engineered systems. But sound isn't the only clue. When radar signals were sent toward the object, subtle modulations in return strength were noted during specific rotational alignments, suggesting that the resonance within 3I-ATLAS may be modulating its radar cross-section, like a vibrating string affects reflected light. In other words, the standing wave isn't just internal, it's interacting with external signals. What could create and sustain such waves? There are three theories. The first is accidental geometry, that the object's internal shape happens to support resonance. The second is material composition, some exotic alloy or crystalline structure with low damping properties. The third and most troubling is purpose, that the structure is designed to maintain these waves, possibly as a stabilizing mechanism or a form of energy distribution. But there is one final layer. During the last observational pass, the amplitude of the standing wave shifted, ever so slightly, in response to solar flare activity, as if the object were listening or responding. In physics, standing waves represent balance, equilibrium between energy and structure. But on 3I-ATLAS, balance does not look passive. It looks deliberate, and in space, nothing echoes without walls to hold the sound. Ice is the defining trait of a comet. It's what sets them apart from dry asteroids and metallic bodies. Ice sublimates, reacts to solar heat, and creates tails, jets, and outgassing phenomena that can be seen across millions of kilometers. Every known comet in recorded history, from Halley to Hale-Bopp, carries frozen volatiles in its core. These include water ice, carbon dioxide, ammonia, and methane. Even in interstellar bodies like Oumuamua, traces of sublimated volatiles were detected or expected. But 3I-ATLAS breaks that rule. It's not just missing ice, it's missing ice in the exact places where ice must exist. On November 17th, a joint team from China's Tianwen-3 orbiter and the James Webb Space Telescope performed synchronized spectral analysis of 3I-ATLAS. The primary objective: identify signatures of hydrogen, oxygen, and carbon-bearing volatiles near the subsurface layer. The team used deep field infrared mapping, which detects the telltale absorption dips of common ices even through layers of dust or debris. The result was not ambiguous. There was no water ice, no carbon dioxide, no trace methane, no ammonia frost, not even frozen sulfur or nitriles. At a depth of 28 meters, where solar heat should not reach, the internal cavity walls were expected to trap primitive volatiles, locked in place since the object first entered the solar system. But those layers were bone dry. In fact, spectral reflectance showed thermal insulation, with temperature gradients too low to allow sublimation, but too high to preserve primordial ice, unless the walls were actively managing their thermal state. This contradiction led to the first problem. Either the ice had sublimated unnaturally fast, or it was never there to begin with. The first theory collapses under scrutiny. For outgassing to explain the loss of ice, astronomers should have observed a coma, the visible halo of vapour and dust that forms around comets nearing the Sun. But 3I-ATLAS never developed one, not even faint. It remained inert, cold and dry, while passing within ring 3 AU of the Sun's surface. That's physically implausible. At such proximity, even rocky asteroids can develop surface vapour trails. For an object of this size and apparent density to shed no vapour at all suggests that either 1. Its composition is entirely non-volatile, or 2. Something is regulating its surface to suppress evaporation. This brings us to the second theory. 3I-ATLAS never contained ice in the first place. That would make it not a comet, but something else entirely. But then why does its shape, mass and orbital dynamics mimic a comet so precisely? One explanation, proposed by researchers at the University of Tokyo's Astromaterials Lab, suggests that the cavity walls are composed of regolith-coated alloys, porous but non-volatile materials that absorb heat slowly and reflect it in controlled spectra. These materials could simulate the thermal behaviour of ice but lack the mass loss associated with sublimation. If true, then the structure of 3I-ATLAS is thermal camouflage, a system built to simulate comet-like properties without any of the instability. To test this, scientists used a focused mid-infrared pulse from the ESA Solar Sentinel array to induce surface excitation, essentially heating a small patch of the object and watching for a chemical response. Again, there was none. No vapour plume, no molecular fragments, just a slight shift in thermal emission, like heating ceramic, not ice. And this leads to a darker realization. The absence of ice isn't just a missing trait, it's a missing fingerprint, the thing that allows astronomers to date objects, classify them, and trace their origin. Without ice, we can't determine how long 3I-ATLAS has travelled. We can't prove if it's natural or synthetic. We lose all thermochemical context. In short, we lose our ability to understand it. No ice means no history, no origin, and no decay. What remains is a hollow, heat-resistant body that mimics motion, that defies every rule of what a comet is supposed to be. Natural bodies don't grow in perfect layers. Whether a planet, asteroid or comet, time, impact and entropy lead to chaos beneath the surface. Older material compresses beneath newer deposits, impacts fracture symmetry. Heat from solar radiation and internal decay create gradients of density, pressure and texture. Stratigraphy, the study of layers, is a record of that natural disarray. But in 3I-ATLAS, the layers are not chaotic. They are aligned, they are even, and they are impossible. On the morning of November the 17th, high-resolution gravimetric data from the Tianwen-3 polar sweep revealed something few had anticipated, a repeating density structure beneath the surface of 3I-ATLAS. Using reflected gravimetric waveforms and neutron resonance profiling, researchers identified no fewer than 11 concentric layers wrapped around the hollow core. Each layer was spaced exactly 4.6 meters apart. At first, this pattern was considered a scan artifact. Gravimetric reflections can sometimes produce ghost layers due to equipment feedback or motion distortion. But after multiple verification passes, using different instruments at different scan angles, the result held. Every scan showed the same consistent pattern, equidistant bands encasing the cavity like the rings of an onion. And yet these weren't just density lines. They had composition differences. When the Tianwen-3 probe performed pulsed neutron spectrometry, it revealed slight but repeating variations in atomic structure. The innermost layer had higher boron and nickel content, while outer layers showed shifts toward lighter silicates and trace elements like vanadium and titanium. These weren't random mineral distributions, they followed a pattern, a gradient not of time or temperature, but of function. This created an uncomfortable realization. If these bands had formed naturally, as via sedimentation, impact layering or freeze-thaw cycles, they would be irregular, angled, disrupted. We would expect collapsed zones, uneven spacing, compression faults, or oblique seams. But none were present. Even around microfractures and surface scarring, the layers remained perfectly parallel. More disturbingly, they were complete. No partial arcs, no disruptions. The layering wrapped the cavity with near-spherical precision, confirmed by overlapping tomography models from ESA's orbital seismology relay. It was like scanning a synthetic object, one with internal casing, shielding or reinforcement designed to withstand pressure or isolate function. That opened a dangerous new hypothesis. In terrestrial engineering, equidistant layers with compositional variation are found in two primary applications: armor plating and heat shielding. These structures are built to manage directional stress, to protect what's inside or maintain equilibrium under extreme thermal variation, and when layered around a cavity, their purpose becomes clear: containment. But what is being contained? If 3I-ATLAS is hollow, and if its inner wall is lined with tuned microwave-absorbing rings as previously observed, then the outer structural layering may serve to stabilize or protect an internal mechanism, not a biological core, not a ball of ice, but something that shouldn't be exposed, either to us or to the external environment. Researchers at the Instituto de Física Espacial in Madrid proposed a chilling theory. They suggested the layers might act as acoustic insulators, each tuned to a specific harmonic node, effectively silencing internal resonance from escaping the shell. If true, then the layers are not passive. They are active components in a containment system, built to manage sound, vibration, or even shock. But regardless of theory, one fact remains. No known natural body displays this kind of internal symmetry. Not asteroids, not moons, not planetary cores. This is not the result of time, pressure, or heat. It is the result of placement. And in nature there is no law that forces material to deposit itself every 4.6 meters, with changing atomic profiles, and wrap it flawlessly around a hollow void. This is not geology, Its architecture, and whatever 3I-ATLAS was meant to contain, it was built layer by layer, not by the cosmos but by design. When energy enters a structure, it must go somewhere. In astrophysics, this principle underlies everything from impact craters to seismic ripples on moons. A strike, a pulse, a thermal spike. They all leave behind traces, and when it comes to vibration, those traces often remain in the form of deformation, fractures, or internal stress. But 3I-ATLAS absorbs vibrational energy without damage. Worse, it absorbs it intelligently. On November 17th, a team from the German Aerospace Center, DLRs, deployed a synchronized acoustic excitation test. A burst of directed vibrational energy, similar to sonar but tailored to low-frequency elastic modes, was emitted from both Tianwen-3 and the ESA's heliospheric relay node. The aim was simple: stimulate the structure of 3I-ATLAS, observe how the vibration travels, and measure what bounces back. The response was immediate and deeply unnatural. The incoming signal penetrated the outer layers, but no backscatter returned. Instead of reflecting or transmitting, the vibrational wave vanished, as if swallowed. No recoil, no harmonic echo, no measurable surface deformation. For several seconds, instruments recorded total acoustic silence within the object. Then, slowly, a delayed response emerged. Not chaotic like a crumbling rock, but structured. A decaying harmonic, soft and low, peaking in a 3.2 Hz band and then disappearing again. This wasn't a rock reacting to stress. It was a system processing vibration. To rule out scan interference, the team repeated the test at higher intensity. This time, data showed a clearer profile. The energy had not disappeared. It had been rerouted, travelling into internal layers where it was gradually neutralized. The process resembled a mechanical equivalent of noise cancellation, where incoming vibrational waves are neutralized by counter-oscillations inside the shell. In terrestrial engineering, this concept is called active damping, a method used in submarines, spacecraft, and architectural megastructures to minimize stress, prevent resonance buildup, and extend structural integrity under long-term strain. But here's the catch: active damping requires design. It requires an internal logic, a matching of material properties with spatial geometry, to ensure that energy isn't merely absorbed but dispersed without cost. And yet, 3I-ATLAS does this without showing any material degradation. Most natural bodies lose mass under repeated stress. They chip, flake, or shift. But analysis of the scan site after 3 acoustic pulses showed no changes in albedo, mass density, or mechanical stiffness. The object had absorbed the vibration, processed it internally, and left no scar. The implications are staggering. If a body can absorb acoustic energy, whether from micrometeorite impact, solar wind compression, or internal mechanical events, and remain unaltered, it suggests a level of internal organization not found in any known comet or asteroid. Further modeling by the MIT Space Structures Laboratory revealed that for such damping to occur across a wide frequency band, the cavity and its shell must contain graded material layers, each optimized for a different resonance window. These meta-layers would shift energy along radial paths, converting longitudinal stress into torsional or shear damping, like a spiral maze that unwinds a pulse without ever breaking it. No known geological process produces such structures. No random collision history leads to them. This is a mechanical profile, not a natural one. Moreover, when the object was later struck by a solar windshock wave from a mild Class B solar flare, it did not react with turbulence or vibration. Instead, the acoustic signature dropped to 0 again, only to rebound after the flare had passed, releasing stored mechanical energy in a controlled, delayed pulse. It was like watching a vault door bend slightly, hold, and then return to shape. In conclusion, 3I-ATLAS does not passively exist in space. It interacts. It absorbs without loss. It responds without chaos. And in the silence after vibration, it whispers something deeper. That energy, too, can be managed like thought. Tidal flexing is not rare. It's expected. When a celestial body passes near a star or planet, it experiences gravitational differentials. Stronger pull on the near side, weaker on the far side. This stretching force causes internal deformation, subtle shifts in mass, heat generation, even the cracking of crusts. It's how Jupiter's moon Io creates volcanic activity. It's how comets fracture near the Sun. But 3I-ATLAS did not flex. On November 17th, the object passed through a region of solar tidal gradient between 0.3 and 0.2 astronomical units, close enough that its leading and trailing hemispheres should have experienced measurable tidal forces. Instruments from the ESA Solar Inertial Observer and Tianwen-3 gravimetry arrays were perfectly positioned to detect the resulting effects: mass displacement, structural bowing, or vibrational torsion. Yet every sensor recorded the same thing: no deviation, no stretching, no compression, not even microflex at stress points. This absence of tidal response is not just rare, it's inconsistent with everything we understand about how matter behaves in dynamic gravitational fields. Even solid iron asteroids exhibit tiny shape changes under tidal influence, but 3I-ATLAS behaved as if it were immune. To explain this, researchers from the Caltech Planetary Mechanics Group developed a dynamic flex model. It showed that for an object of 3I-ATLAS's mass and volume to resist tidal deformation entirely, one of three things must be true. It is unusually light, too insubstantial to generate internal stress gradients. It is unusually stiff, composed of ultra-rigid material that deflects gravitational influence. It is not behaving as a solid body at all. Each explanation contradicts something we already know. First, the mass. Radar density and orbital perturbation data place 3I-ATLAS's mass well above the limit for low-density bodies. It has gravity. It influences nearby dust fields. It even subtly perturbs satellites when passing nearby, so it's not light. Second, stiffness. While we cannot directly measure internal rigidity, the damping behavior seen during acoustic scans contradicts ultra-rigidity. The object absorbs vibration. It reacts elastically. It has flexibility, but only when it chooses. That leads to the third, more disturbing conclusion. 3I-ATLAS may possess adaptive structure. In this model, the object does not behave like a rock or metal sphere. Instead, it reacts to external gravitational gradients through internal counterforces, possibly via layered damping shells, controlled mass redistribution, or inertial balancing systems that cancel the flex before it begins. It would be like a bridge that senses an earthquake and reshapes itself so the vibration never builds. There is one supporting clue. During its closest pass to the Sun, researchers detected a transient internal heat bloom, not at the surface where solar radiation would hit, but deep inside near the cavity. The temperature rose by 2.1 degrees Celsius, remained stable for 5 minutes, and then dropped again. There was no visible jet, no vapor release, just a silent symmetrical warming. This thermal pulse occurred exactly 29 seconds after the peak tidal gradient. To engineers at the Université de Strasbourg's Space Design Lab, this resembled a thermal compensator, a core that momentarily absorbed flex energy through phase change material or heat distribution lattices, then released it harmlessly. If correct, this is not passive shielding, it's feedback control, a structural response system calibrated to tidal environments. This would mean 3I-ATLAS isn't just surviving tidal forces, it's anticipating them. But why build such a system? One reason stands out: to preserve what's inside. If the internal cavity holds sensitive geometry, reflective chambers, pressure nodes, or computational material, then even minor tidal stress could ruin it. So the object must remain still, even while falling toward a star. In space, stillness is unnatural. Movement is constant. Flex is inevitable, unless you're built not to move. And on November 17th, 3I-ATLAS didn't bend, didn't crack, didn't even flinch. It passed through a tidal corridor like a fixed point in gravity. And in that stillness, it spoke the loudest anomaly of all. Of all the anomalies surrounding 3I-ATLAS, none is more fundamental, or more unsettling, than this. The core is hollow, and that hollow should not exist. Not there. Not at that depth. Not with those properties. On November 17th, following a full suite of radar tomography, passes by Tianwen-3, reinforced by delayed reprocessing from ESA's deep scan array, the full internal structure of 3I-ATLAS became undeniable. The object contains a central void, nearly perfect in geometry, 21% of the total diameter, located precisely at the gravitational midpoint. This revelation did not arrive in isolation. Previous chapters had already catalogued the disturbing signs, the microwave echo delays, the acoustic absorption, the absence of ice, the architectural layering. But this was different. The void wasn't an anomaly in behaviour. It was a physical fact, a massive hole suspended in the middle of a body travelling tens of kilometres per second through interstellar space, and somehow remaining intact. It breaks everything we know about material stability. In normal astrophysical bodies, whether comet, asteroid or rocky planetoid, a hollow cavity at the centre is inherently unstable. Gravitational compression alone should collapse the walls inward. Even porous carbonaceous bodies, riddled with voids and fractures, eventually compact toward their centres. Central hollows do not survive orbital pressure, tidal flex or micro-impacts. But 3I-ATLAS not only sustains its hollow core, it preserves it. Researchers from the University of Oslo's Applied Materials Division ran structural simulations using all known silicate, metallic and composite compositions observed in deep space. None could support a central void of this size under normal motion without warping, collapsing or shedding mass. Yet 3I-ATLAS has shown zero deformation through its journey across the heliosphere, despite multiple close passes with gravitational bodies. So how is the void still there? One possibility is internal scaffolding, a lattice or exoskeletal framework maintaining cavity integrity under dynamic loads. Another is active balance, where the object's mass is distributed in such a way that gravitational forces cancel out internally, leaving the hollow in mechanical equilibrium. But both theories require intention. Design. Precision beyond what natural accretion, impact or erosion can achieve. To understand the consequences, consider what the hollow core means. It is not a product of random internal decay. It is not a remnant of an impact that excavated inward. There are no signs of entry points, surface craters or collapse rings. It is not a frozen bubble. No ice, no vapour, no trapped volatiles. It is clean, it is centred, and it is structured. In short, the hollow core isn't just a missing chunk of matter, it's a feature. Further investigation by the Harvard-Smithsonian Center for Astrophysics suggested a hypothesis more complex than any previous model. They proposed the cavity may act as a resonant void, a central zone that by being empty serves a higher purpose, amplifying, dampening or modulating physical forces like vibration, temperature or electromagnetic energy across the surrounding shell. In engineered systems, such cavities are used in things like waveguides, acoustic lenses or heat isolators. But to build one the size of a mountain and set it travelling through interstellar space would require not just advanced materials, but an understanding of space physics beyond our own. Some now question whether 3I-ATLAS is a vehicle, a signal amplifier, or a failed containment unit. But the object offers no answers, only perfect silence inside a void that refuses to collapse. Nature doesn't build hollow cores like this. Nature fills voids, gravity crushes them, time erases them. But 3I-ATLAS maintains one, precisely, geometrically, and with utter stillness. And the hardest truth to accept is this: the hollow core shouldn't exist there, but it does. And now that we've found it, we may never be able to unsee what that implies. What we have discovered is not just an absence of mass, it's an absence of explanation, a structure that cannot hold, a silence that shouldn't exist, a cavity where gravity demands collapse. Whether this is natural, designed, or something in between, we now know one thing with certainty. 3I-ATLAS does not behave like any comet, asteroid, or wanderer we've ever seen. And if a hollow core this perfect exists where no void should, we must ask, what else is inside? We'll be watching closely.